Hello and welcome to a look at transitives and transversals. We're going to look at the transitive and substitution properties, which are pretty new to us. And then we're also going to look at transversals, which we have seen before, but we're going to look at them in a little bit of a different light so that we can start talking about them in our proofs. So to start us off here, let's remember that all this really came from this guy Euclid. And Euclid is considered to be the father of geometry. He put together, if he did not create himself, a very large portion of the basis of what we call geometry today. So he did this 2,000 years ago without really any modern technology, and he was able to do it just fine. I have absolute faith that if he can do this, then you should be able to do the same. Here he is, I believe this is in front of a building in Britain, where his body was frozen in carbonite, and he looks down upon us all to this very day. So for starters here, let's take a look at the transitive property. And transitive property, when you think about it really, it's actually quite simple. So suppose you've got a relationship such as the line segment AB is congruent to line segment CD. Okay? So we know those are congruent to each other. Now you're given another piece of information, that the line segment CD is congruent to the line segment EF. Well, let's think about this for a minute. If AB is congruent to CD and CD is congruent to EF, well, all that tells us is that AB is going to be congruent to EF, and that is the transitive property. And this makes sense, right? If one thing is congruent to another thing, and a third thing is congruent to the second thing, they're going to be all congruent to each other. Okay? They're all congruent to each other. It's like a chain. If AB is congruent to CD and CD is congruent to EF, they are all going to be congruent to each other. That's the transitive property, okay? And its brother here is the substitution property. Now, the transitive property is talking about congruence. Substitution property is talking about numbers, talking about measures in this case. So if we've got AB equals CD, remember when we don't have the line segment symbol above here, we're talking about the length of AB. So the length of AB is equal to the length of CD. And the length of CD is equal to the length of EF. Okay, can you see where we're going with this right now? What's going to happen next? If you said that AB is going to equal EF, you are absolutely spot on. Both AB and EF, both of those lengths, are equal to CD. So since they're both equal to CD, they're both equal to each other. That's all the transitive and substitution properties are. So we will be using those. I think once you think about it a little bit, if this didn't make sense the first go around, pause it, go back, check it out again. But this is something that really we're going to be using a fair bit of. So if you don't get it right away, I'm sure within like the next day or so. We'll talk about it more in class. Okay? So that's the new stuff. Let's look a little bit at a quick review. We remember that we have these transversals. Transversals are lines that intersect a pair of lines or more. Okay, so we've got the transversal there highlighted in red. That's cutting through two lines that don't quite look parallel. Don't get them confused with transformers. Transversals are not transformers. Don't make that confusing mistake, otherwise you could find yourself in some trouble. Totally different. Totally different. Although in this case, both of them do look pretty good in red. Okay, moving on. So here we've got a number of angles that are formed when the transversal T cuts through lines M and N. Okay, they're numbered 1 through 8. We've got interior angles. Interior, in other words, simply being inside. So these are our interior angles, 4, 3, 5, and 6, because they're on the inside. That leaves us with 1, 2, 7, and 8, which we will call what? which we will call our exterior angles. Those are on the outside. So it's very important that we've got this terminology down. Again, we've seen this before, just a quick review. Now, the following is true for transversals cutting through parallel lines only. That's a direct quote from Tom Selleck, actor, most notably of the TV show Magnum P.I. It was a groundbreaking show. So, true only for transversals cutting through parallel lines only. There's special relationships that come when we've got a transversal that cuts through parallel lines. Okay, such as alternate interior angles. They are congruent. Whoop, and there the arrow just moved because that is a much better alignment there of alternate interior angles. 3 and 5, as we can clearly see, they're on the inside, they're on the interior, but they're on opposite sides of the transversal. That's what makes them alternate. And again, we've seen this before. They're going to be congruent. They're going to have the same measure. 3 and 5 are going to be congruent. What other pair here is going to be congruent as well because they are alternate interior angles? 6 and 4. Angles 6 and 4 are also going to be congruent in this case. We have a similar relationship that happens for exterior alternate angles. And this kind of makes sense when you start thinking about the relationship to vertical angles. So angle 1 and angle 7, alternate exterior angles, are going to be congruent. What other pair here of alternate exterior angles do we have? 2 and 8. And those are also congruent. Now, this one's a little different. When you've got the same side interior angles, they're not going to be congruent. Okay? I suppose there's one case where they could be congruent if you've got 90-degree angles running all around, but that's quite rare and, to be quite honest, quite boring, really. So if one is less than 90, the other one's got to be greater than 90. Alternate interior are going to be congruent. But if they're the same side interior, they're supplementary. And supplementary, again, means what? Yeah, it means that they've got to be 180 degrees when added up together, their measures. So, same side interior, those are going to add up to 180. Now, we're going to start to use these relationships in proofs. So let's take a look at this guy. We're given that line M is parallel to line N, with the angles as numbered. It says prove that angle 6 is congruent to angle 4. Well, how about this? We have all of our conclusions laid out here. Our first conclusion, M is parallel to N. Well, what's our justification for that? Given. Given, given, given. When we're setting up two-column proofs like this, given is, well, given. Angle 6 is congruent to angle 2. What can we say about that? Well, corresponding angles are also congruent. We looked at corresponding angles as well. 6 and 2 are our top right angles. Okay, in each pair, out of 5, 6, 8, and 7, the top right one is 6. Out of 1, 4, 3, and 2, top right one is 2. So there's the corresponding angles postulate that tells us that, hey, these guys are going to be congruent because they match up, they correspond. They're both in this case, the top right. Angle 2 is congruent to angle 4. Well, why would that one be true? This is vertical angles. Vertical angles postulate. They are congruent. So we know that those are equal. And now we can say that angle 6 is congruent to angle 4 because the transitive property. Notice both angle 6 and angle 4 we proved to be congruent to angle 2. Since we know that 6 and 4 are congruent to angle 2, then we can say that by the transitive property, they are congruent to each other. And that's it. And then we're done. We're done. That's why the transitive property is so awesome. This is really handy one to know the corresponding angles postulate, which we just used. This is actually back on page 146 in your book. Basically talks about how you've got two corresponding angles. If you've got the same measure, then the lines are going to be parallel. And similarly, if the lines are parallel, then the corresponding angles have the same measure. Remember, we started this section off by talking about we're focusing on a transversal cutting through parallel lines. You will see this a fair bit. This is a pretty common thing. You can also use this to prove if two lines are indeed parallel by checking the angles made by a transversal that cuts through those two lines. Okay, so very useful, very useful. Put a sticky note or something on page 146 of your book, or take a picture of this, or memorize it, or whatever floats your boat. Another example here. So we've got to prove the alternate exterior angles theorem using the figure at the right as a drawing. So we're given that angle 5 is congruent to angle 3. We've got to prove that M is parallel to N. Okay, here's exactly one of those cases where we've got to prove two lines are parallel by using what we know. So angle 5 is congruent to angle 3, given. Okay? Say that angle 3 is congruent to angle 1. What's our reason for that? We just saw it. Vertical angles theorem. Vertical angles, because they are vertical angles. So we can call them congruent. Angle 5 is congruent to angle 1. Well, what's the connection there? Those two angles are corresponding. So, if angle 1 is congruent to angle 3, and angle 5 is congruent to angle 3, our transitive property of congruence tells us that angle 5 is going to be directly congruent to angle 1. And they are corresponding. So if two corresponding angles have the same measure, then the lines are parallel. That's our corresponding angles postulate that we just looked at. So since really the crux here of being able to prove that M is parallel to N is once we've got angle 5 congruent to angle 1, once we've got corresponding angles being congruent, then we can make that leap by the corresponding angles postulate to say that the two lines are going to be parallel to each other. Here are some very good justifications that we will be using pretty regularly on page 273. So sometimes you are given parallel lines, sometimes you need to prove the parallel lines. Check this out in your book, it will be extremely helpful. We're going to be looking more at proofs, so don't think this is by any means the end. There is more to come, but make sure you've got this down. Watch it again briefly, or look at the highlights if you need to, and let me know if you have questions. I trust you guys will do well with this, and I'm here to help you if there's anything that's causing any hiccups. Proofs can be a little bit wacky once you first, get into them. But we will absolutely get there. So I hope you enjoyed this. Hope this was helpful, and have a good day.